All right, so going through Unit 10 review packet. So the first thing I'm going to do is fill in your compounds quiz table. So again, you should know all 12 boxes here. I will blank out 4 random ones. This is not me saying this is exactly how it's going to look like. So you need to know every box, even the ones you don't fill in. But the common name for hydrochloric acid or HCl is muriatic acid, just spelled MURIATIC and then acid. And remember, spelling does count here. Then, when we're talking about natural gas or methane, the chemical formula for that is CH4. Then we have what's called wood alcohol, but the systematic name for that is methanol. There's an H there. And so we give that chemical formula CH3OH. And then we have grain alcohol or ethanol, which is C2H5OH. All right, now moving on. So this first problem I kind of hit really hard with theory right away. And so I want to make some connections with you. And this is what I was hoping to get from this question is, okay, if we have a sample that contains 6.02 times 10 to the 23 atoms, what does this number look like? Hopefully, you're thinking Avogadro's number. And so Avogadro's number, remember, is the definition of how many atoms are in 1 mole. So we know just by telling us how many atoms we have that we have a mole of a substance. Now, you need to start thinking about, okay, well, what does grams have to do with moles? That's molar mass. So what I expected you to do is read and see how many atoms you have, make the connection that that many atoms is Avogadro's number, aka you have 1 mole. So if we have 1 mole, how can we use our periodic table to figure out what element we have a mole of? Well, you have to know that molar mass is literally defined as the grams per 1 mole. These are the numbers we get off the periodic table. So you were supposed to figure out which element had their molar mass listed. That would be option C. All right, number 2, we are talking about representative particles. And so we need to remember that the 3 options are atoms, molecules, and formula units. And so talking about what defines which atoms, we use this when we have elements. So if you see something that is not bonded to anything else, there's just one element, quantity 1, we're going to use atoms. So looking on the left-hand side here, options A through F, there should be 1 that gets atoms as its representative particle. Hopefully you chose nickel. Now, anything else that has bonds or at least 2 of the same element are either going to use molecules or formula units. These represent some sort of compound. We just have to decide what type of compound they are. So if you're a molecule, you're going to be covalent. And if you're a formula unit, you're going to be ionic. So this tests your knowledge of remembering what covalent and ionic are. And you're going to have to know what types of elements live where on the periodic table. So covalent are non-metal bonds. Ionic are a metal and a non-metal. You will not see metal-metal bonds. So now you have to go through and decide for each one of these, is it a non-metal non-metal or a metal and a non-metal? And so the key is to remember the non-metals live on the upper right corner, plus hydrogen, which lives on the left side. So hydrogen's tricky. Even though it's on the left side of the periodic table, it is a non-metal. So non-metals, upper right corner, and hydrogen. And then the rest are metals, because this all depends on what side of the staircase they're on. So if we're looking at CO2, both of these are nonmetals. They live on that upper right side of the periodic table. So if they're both nonmetals, they're covalent and get molecules as their representative particle. O2 means that you have a bond between 2 oxygens, which is a bond between 2 nonmetals, therefore will also get molecules. KCl. Well, potassium, or K, is a metal. It lives on the left-hand side of the table. Chlorine is a nonmetal, so this is ionic, so it'll get formula units. Like I said, for the next one, hydrogen is tricky because it lives on the left side of the table, but it's an exception. It is a nonmetal. So technically you have two nonmetals molecules. And lastly, both carbon and hydrogen are nonmetals. Again, molecules. All right, moving on. This is just a definition. Can you tell me what molar mass is? Well, the molar mass is just the sum. So we're not dealing with anything with products. We're always adding here. But it's not the sum of atomic numbers, but the masses of its atoms. So A is the correct answer here. 4. So 4, this is kind of a review of, kind of brings us back to balancing. I just want to make sure you guys know how to distribute things when there are parentheses involved. So we always want to distribute to the inside of the parentheses if there's a subscript right outside. Notice how it does not reach Fe or iron. So we have 2 atoms of Fe, 3 for sulfur, and it's multiplication, not addition. So we have 9 oxygen atoms. All right. This is just a refresher of what we should have or what my expectations are for your work. You need to make sure that you always have a unit. So moles, grams, molecules, etc. You need to make sure that you always have an element or compound name. When in doubt, put the element and compound name on every number. Make sure you have a unit on every single number. Molar masses need to be rounded to the tens place. I can't emphasize that enough. And then I need to see your guys' conversion fractions. I do not want to see just straight line. I need to see a numerator and a denominator when you're using these. And just be aware of sig figs. Okay. These I just wanted you to figure out what was wrong. This first one, there's a couple things that I would have taken points off. The largest one is the fact that this is not written as a conversion factor. And so what I would have want to see with this, so 1, it's not a conversion factor, and 2, there is no type of element or compound listed here. So what if you were to set this up, it would be 5.2 moles of O2. That's what you start with. But then instead of writing 2G slash mole O2, it would be 2G O2, 1 mole O2. So this is obviously not the correct numbers, but mostly I wanted you to recognize that this was not written in a fraction. The second one here, we're just missing that H2 on the bottom. Third one here, this one was a little tricky, but when we're dealing with molar masses, which is this type of conversion fraction here, if this is a molar mass, is it rounded to the tens place? No. So what should be there is 27.0. So this should be 0.0 after that 27. All right, so now we're going to get into adding molar masses of things. And so we first have to think of the quantity. So when I do the molar mass, I figure out how many irons, how many sulfurs, how many oxygen. So I know I have to distribute this 3. We have 1 iron, 3 sulfurs, 9. 3 times 3 is 9 oxygen. So make sure you're not adding. 1 iron weighs 55.8 grams per mole. 1 sulfur weighs 32.1 grams per mole. 1 oxygen weighs 16.0 grams per mole. So if we add up these things together, this stays at 55.8 grams per mole. This one now becomes 96.3 grams per mole, and then the oxygens become 144.0 grams per mole. If you add up everything here, that will give you answer, A. All right, number 6. This is asking how many grams of CO2 are in 3.5 moles. So the rest of these problems are going to be stoichiometry on this page. And so what I was trying to emphasize yesterday during our review time is that you have 2 tools now. You have your molar mass, which has units of grams per mole, and you have Avogadro's number, which has units of molecules, atoms, formula units, per 1 mole. So it's going to be up to you to decide, are you using Avogadro's number or molar mass? So the key is the units that we see here. If we see things that say grams, and I'm going to go through and highlight throughout these problems. Number 7, anything talk about G, grams, or mass? No. How about 8? Yes, we talk about grams again here. 9, we talk about mass. All of these problems are going to use molar mass then. Now, if you see anything that talks about molecules, atoms, formula units, we use Avogadro's number. 6, no. 7, yes, we talk about molecules. 8, we talk about molecules. 9, we talk about atoms. So I know I'm going to use Avogadro's number for all these problems. So the first 2 are single step problems. I only have 1 tool highlighted. 8 and 9 are double step problems because 2 of my tools are highlighted. So I'll start with the first one here then. If I see grams, right away I know I need to find molar mass. So I'm going to find the molar mass of CO2. If you calculate this out, you would get 44.0 grams per mole. I'm just not going to calculate it. You should know how to do that by now, just to be quick. So for these problems, I always start with the quantity given. Well, you were given that you have 3.5 moles. So start with 3.5 moles. And then you're going to tell me what it is. This is moles of CO2. And you're going to get ready to set up your conversion fraction here. And so we're using grams, or we're trying to figure out grams, which means we need to use our molar mass. Now we have to decide how we're using it, because remember, we can either use this molar mass as 44.0 grams per mole, or we can use it as mole over 44 grams. Notice how the 44 always stays with the grams term. So make sure that your number that you calculate always stays with the grams, because molar mass is the definition of how many grams per 1 mole. So your mole will always have a value of 1 for these problems. Now, if we want to get moles to cancel, do we want to use option number 1 or number 2? Hopefully you chose number 1. That is the correct answer. So we will multiply by 44.0 grams per 1 mole. And so this is both CO2. So we're still working with CO2. So we can cancel our unit of mole. We're left in grams. That's awesome. And so you calculate this out. You should have gotten option B. All right, number 7. So here we have molecules, so we're using Avogadro's number. So I'm just going to write out Avogadro's number. This is defined as 6.02 times 10 to the 23rd molecules in 1 mole. And so remember, this can also be written as 1 mole over 6.02 times 10 to the 23rd molecules. So it's going to be up for us to decide, do we use option 1 as our conversion fraction or option 2? And so how we're going to do that is we're going to start with what we know. We know we have this many molecules of HCl. So if we start with 12.5 times 10 to the 23rd molecules of HCl, and we're going to set up our conversion fraction. You can think of it 2 ways. 1, what's our target unit? Well, our target unit is moles. If our target is moles, we put the target on top. We know that we want the unit of mole on top. Well, that matches option number 2 for using Avogadro's number. So we're going to put 1 mole, and remember, we're still working with HCl. And so in 1 mole of HCl, we have 6.02 times 10 to the 23rd molecules of HCl. If you calculate that out, you would get A as your answer. All right, so starting with number 8, this is our first 2-step problem here. And so the key is, when you read this problem, does it mention moles anywhere? No. So we know at some point, but before we can get to the ultimate target, we need to go to moles first. So I always like to think about what my track is going to look like. Well, what number are we starting with? we're starting with 127 grams of something. So if we're starting with grams, we always have to go to moles and then lastly get to molecules. So this is going to be like my track I'm going to take for this double conversion, because we're going to need some sort of conversion going from grams to moles, and we're going to need another conversion going from moles to molecules. So we're using both tools for this example. Now, again, I know I'm working with grams. I immediately going to have to find the molar mass. So if you figure out the molar mass, now we're working with iodine, which is I2. So you need 2 times the mass of iodine, which would give you 253.8 grams per mole. All right, so here is one tool. This is my molar mass tool. And remember that Avogadro's number is going to be our other one as well, but we'll come back and assess that. So starting with what we know, I circled it in the problem. We know we have 127 grams of I2. So thinking of our first conversion, we have to go from grams to moles. That's our molar mass. So are we using our molar mass as is, or are we going to switch quantities and put moles on top and grams on the bottom? Hopefully you said switch or flip it. So we want grams to cancel. So we're going to put the 253.8 grams that are defined for I2 and then 1 mole of I2 on top. Okay, so we are done with this first conversion here. So now we're going to set up the second one. The second one says, okay, well now we're in units of moles, which we'll double check. Okay, this grams cancels with this one. Great. Yep, we're in units of moles. And so now we have to go from moles to molecules. Well, how do we do that? Avogadro's number. So we think of Avogadro's number. If we look up here, our 2 options are these 2. Option 1 being molecules over mole, option 2 being mole over molecule. So if we want moles to cancel, or if we know our target is molecules, which one are we going to use? Hopefully you said number 1. So we're using I'll change the color back. 6.02 times 10 to the 23rd. That's how many molecules of I2 there are in 1 mole of I2. So now we can cancel out moles of I2. With moles of I2, we're left with molecules of I2. And the way I type this in my calculator is 127 divided by 253.8 times 6.02 times 10 to the 23rd. So you always multiply by everything that's listed on the top of the fractions, divide by everything that's on the bottom. If you do that, you should get B as your answer. All right, number 9. This one's asking what the mass is of so many atoms. So again, we don't talk about moles at all, so we know it's a double conversion. And so if we think about the number we start with, we're starting with how many atoms of something we have. So we start with atoms. Ultimately, we want to get to grams, but we have to go to moles first and then grams. So grams or mass. So we know we are going to need the molar mass of copper because we need to figure out a mass of it. And so if you look it up on the periodic table, the molar mass of Cu is equal to 63.5 grams per mole. All right, so let's start with what we know. We know that we have 8.3 times 10 to the 25th atoms copper. Now, our first conversion here is going from atoms to moles. So does Avogadro's number or molar mass deal with atoms? Hopefully you said Avogadro's number. So atoms is our representative particle for this problem, meaning whatever the representative particle gets the 6.02 times 10 to the 20. Sorry, my pencil died. Anyway, so we are going to figure out, we were just discussing, do we put atoms on the bottom or top of this conversion fraction? Hopefully you said bottom, because we want to get those atoms canceled out. So that means we put Avogadro's number, which tells us there are 6.02 times 10 to the 23rd atoms of copper in 1 mole of copper. Awesome. So now atoms of Cu cancel with atoms of Cu. We're left with moles of Cu. That means we are done with this conversion. Our next then is going from moles to grams, which we already decided we need molar mass for that. So if we set that up, do we use our molar mass as is, or do we have to flip it? Hopefully you said as is, because now if we use as is, for every 1 mole of copper, we have 63.5 grams. So grams is our target unit. We want that on top. Our moles of Cu cancel out with moles of Cu here. If you take 8.3 times 10 to the 25, make sure you're putting parentheses around this whole thing in your calculator, dividing it by 6.02 times 10 to the 23rd with parentheses around it, then multiplying by 63.5, you will get an answer that you are like, wait a second, my answer's not on here. It might be 8,750 something. But I just wanted to emphasize, because there's only 2 sig figs here, I could only have 2 sig figs in my answer. So A is the correct answer here. All right, next one here. So the last 2 here have to do with percent composition. This first one here, if I give 0 masses, you know you're going to have to calculate molar masses. And so remember that percent comp is equal to the mass, and in this case of an element, it specifically says sulfur. This one doesn't ask you to do 4 different ones, and then we're always going to put that over the mass of the compound. So the biggest thing here, can you find the molar mass of MgSO4? Well, that is going to be equal to, you have 1 Mg, 1 S, 4 oxygens, so Mg times 24.3, 1 times 24.3, 1 times 32.1, 4 times 16.0, still have 24.3, still have 32.1, then 4 times 16, I think that's 64. Sorry, I'm just doing this off the top of my head. If we add all these together to get our molar mass, you guys should get 120.4. And so then lastly, to set up this problem for percent comp, the mass of all the sulfurs, there's just 1. So that's the 32.1. We're dividing that by 120.4, multiply that by 100, and we get A as our answer. All right, the last one here. Now, we are given masses, so we need to figure out 2 things. Again, mass of element. In our case, this problem asks about chlorine, and we need to figure out the mass of compound. When you are given sample masses like this, those are what you use. Do not use molar mass when you're given masses like that. And so the mass of chlorine is just 67.8 grams. That's what it tells you. The mass of your compound is the mass of these 2 added together. So on the bottom, you have 54.6 grams plus 67.8 grams. And then if you multiply that by 100, you should get C as your answer.